In this video, we're going to look at what happens when we lift a surface parcel. This is shown schematically on the right. Take a parcel of air near the surface and lift it along a dry adiabatic lapse rate. Lift it to with its surface value of mixing ratio. Where the two lines intersect, we have the lifting condensation level. But if the parcel of air is still cooler than its environment, in order for cloud to form, we need to continue to force it upwards. And until we reach the level of free convection, where parcels are freely convecting due to positive buoyancy, any cloud that forms between the LCL and the LFC will be stratus cloud. Above the LFC and below the equilibrium level, or the level of neutral buoyancy, will form cumuliform cloud, and depending upon the depth it'll be cumulus or cumulonimbus. In this case it's a cumulus cloud. So, to summarise, between the LCL and the LFC, parcels have negative buoyancy and have to be forced upwards in order for cloud to condense. But between the LFC and the EL, the equilibrium level, parcels have positive buoyancy because they're warmer than the environment, and therefore we get the formation of convective type cloud. Here's a question. Is the equilibrium level always the top of a convective cloud? Well, what do you think? It depends upon the momentum that cloud parcels have. If they have sufficient momentum, they can punch through the inversion or the tropopause a little way. They'll find themselves in an environment that's where they're negatively buoyant, and so parcels will eventually collapse back down. So the equilibrium level isn't always cloud top. Here's an example of an LCL, LFC and equilibrium level. So for the given forecast maximum temperature and the surface mixing ratio, you can see the LCL lifting condensation level occurs to the left of the temperature profile. And so forced lifting is required between the LCL and the LFC before parcels become positively buoyant and can ascend due to this positive buoyancy until they reach the equilibrium level. So in this case there will be stratus between about 4,000 feet or thereabouts and 10 or 11,000 feet, and convective cloud between about 10 or 11,000 feet and all the way to the equilibrium level at about 33,000 feet. Now, as an exercise, plot up this trace on a skew-T log P aerological diagram, calculate the LCL and the LFC, and ask yourself what cloud type occurs below the LFC, and how would you know what cloud type occurs above the LFC? Pause the video now and carry out this exercise. Well, how did you go? Here's a suggested answer. We see that the LCL occurs to the left of the profile, and so it's going to be stratiform cloud between that and the LFC. The LCL occurs at about 940 hectopascals and the LFC at about 800 hectopascals. So what can cause the lift needed for a parcel to reach the LCL or the LFC? Well, we'll look at that in the subsequent video. So 940 is our LCL, 800 is our LFC. We get stratus cloud between the LCL and the LFC. But we don't know what type of cloud we've got until we can calculate the height, in particular, of the minus 20 degrees Celsius level, which will tell us whether or not we have electrification. In other words, are we going to get thunder and lightning or not?